Good morning and welcome to today's session where we continue our discussion on divisibility. All right. So let's just recap where we are. We are looking at divisibility tests, and we're going to look in general at the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, and stop at 11. And there are comments for the numbers past that, but it gets a little complicated. So our goal is, I guess, twofold. One is to just get a sense of properties of these smaller numbers, because we work with them very often. Properties in terms of what features of a larger number do I need to have in order for these smaller ones to be a part of that number and to play a role in getting to larger numbers. And we'll do that by way of divisibility tests, where I want a way to look at a large number and decide, is it divisible by 3, for example? Ask that question for each one. Without exactly knowing what the quotient and the remainder will be, my question is simpler. Just, is there a remainder? Or does 3, for example, divide nicely, fit nicely into this number, forming one of its building blocks, so to speak? So we have already done 10, 5, and 2, and they were very familiar. Most of us don't even think about checking if a number is divisible by 10, divisible by 5, divisible by 2. We're so used to it. But for a student seeing this for the first time, it might not be that straightforward and obvious. Why do I only need to check the last digit? And then if it satisfies some properties, then I know if it's going to be divisible by 10, divisible by 5, divisible by 2. So 2, 5, and 10 all have similar tests in that I look at the last or the rightmost digit in my number. Meaning the number can be extremely large, only that very last digit, only the ones digit, decides if my number is using a 2, a 5, or a 10 in its building blocks, multiplicatively speaking. And as we progress through this list, the requirements or the test will become a little bit more complicated, and so will the reason for why this test works. You can easily explain by way of an example and convince someone why 2, 5, and 10 have their tests the way they do. But as things get more complicated, examples alone aren't as convincing because things are more complicated. I want to just sort of have an awareness of how things are done properly, deductive reasoning, logical arguments to prove beyond any example that these tests will work. So I just want to be aware of that. I'll make it clear that the proof side of things you do not need to reproduce, but I think it still has benefit to at least just be aware that inductive reasoning, just looking at examples, isn't a proof that the test will always work. It might convince someone and help someone to understand, but it is not a logically sound argument. So Let me just say here, number A, let's call it, is divisible by some number B if there exists a number we call Q for quotient such that I can write A in that quotient times divisor plus 0 here. We've seen this before, but technically divisibility is defined like this officially. If I have two numbers, let's think of A as the larger one and B as the divisor. B is going to divide into A if I can find some number Q that when I multiply it by B, I get A. And there's nothing else I need to add. The remainder is 0. Remainder is 0. Okay. So now from this, I can deduce two properties, which may be a little confusing in appearance, but if we translate it into simple words, as simple as we can, might be better understood. And we're going to need these two properties of divisibility in order to explain why the upcoming tests will work the way they do. So let me do it in general and then see how it makes, if it makes sense, and see if you have any questions. If you have a question in the chat, you don't have to say you have a question, you just ask your question. Feel free to interrupt me, we have time. There is no problem. So, divisibility, right? So, let me say it in words maybe first. Yeah. If I have some number, right? I'm making general statements. I can't look at a specific example necessarily, but afterwards we can. If A is divisible by some other number B, I think of A as my big one, B as my small one, then other way around, then any multiple of A is also going to be divisible by B. Now that's not a terribly hard property to be convinced of, because some examples will probably defend it sufficiently, even though that's not a proof. Let's look at some examples. Examples definitely help, but I need to understand the role that those examples play. If I take, for example, 15 divisible by 5. Let's make it easy. Then 2 times 15, meaning 30, is also going to be divisible by 5. We know this. 3 times 15? Well, because 5, quote unquote, fits into 15, I can stack 15s. It'll fit into that as well. And any multiple. If I look at the official sort of definition of divisibility, if 15 is divisible by 5, officially it's because I can write 15 as some number times 5. There is some number, in this case it's a 3. So if I now look at 2 times 15, I'll be consistent with my times symbols here, then it's going to be the same as 2 times 3 times 5, because 15 is 3 times 5. So if I insert that in here, I get 2 times 3 times 5, which is 6 times 5. So again, there is some q, some number, so that when I multiply it by 5, I get my 30, my bigger number. So you can do it by way of example. I don't want to get too formal, but know that these general arguments that rely on this definition are in the background. So I want to at least show you this one so you know how would a general argument look that proves this property, never specifying what A and B are. So I just want to see it, be aware of it, and then if I'm really interested, it's all in the book. And if I'm not interested, I'm going to let someone else handle that, knowing that it needs to be done somewhere. Oopsie. Okay, so let me prove this one, just so you understand what it looks like. So if A, I'm going to do it symbolically. If A is divisible by B, that's our mathematical way of saying that same phrase, then we know there exists a Q such that, by way of the definition, I can write A equals Q times B. Now, take any multiple of A. Let's call it N times A, right? Because a multiple is just a certain number of times that number, A. Then we can write this new number, N times A, same as we did up here for the 15 and the 5. By replacing A with its more detailed Q times B, I have N times Q times B, which will be N times Q times B. So there exists a number, not Q, but something else, so that when I multiply it by B, I get the larger number I wanted to divide into. So B divides into N times A. And technically that is done. So though examples help me, I don't know if I can take any A and B such that I have divisibility. And it'll always work if I stack the larger number and look at multiples. I don't know that until I have a general logical argument. Okay, so I just want to be aware of it. Never am I going to ask you for this proof. Okay, so if you didn't like it, that's okay. But know that someone somewhere had to go and figure out all these things for me to trust that the property works. And there's one more property. Let me say it in general and then look at an example. If I have my B, how should I say it the most efficient way here? If I have two numbers, I'll call it A1, and A1 is divisible by B. And I have another number, A2, and it's not divisible by B. Then, if I look at adding those two numbers, B is not going to divide into that. And again, you would have to do it in the same general argument. But by way of example, we're going to see examples soon. It's not that bad to convince yourself. This is one of them. And then the other one is if I have my numbers and I have divisibility, and I have divisibility for the other number as well, A2. Then when I add them up, B will always divide into that as well. Take an example here. If I say 5 divides into 15 and 5 divides into 20, then it's always going to be the case that when I add them up, I get 35 in that case. 5 will always divide into that. Because 15 is 3 times 5, 20 is 4 times 5, so this whole thing is 7 times 5. So I always have a multiple of 5. 5 will divide into that. You see? Now, these things have to be done in general, but we just want to be aware, so we're not going to prove all of this. But I need these two properties. I need to know what happens when I add numbers. Well, it depends on what divided into them. If my small number divided into both, then it'll divide into the sum of the two. If my small number divided into one, but not the other, it's not going to divide into the answer when I add them up. All right. Sometimes we need to think about these things a little bit, but we need these guys for our upcoming divisibility tests. And then we have this one, that if I divide into a number, then I'll automatically divide into any multiple of them. Okay. So, I mean, this topic of number theory is a difficult one. We sort of peek in and then walk away because we don't need more. But know that there is a lot, and it is not simple. To prove properties of numbers in general, integers, I mean, it's not easy. Divisibility test for 4 is next. Now, instead of me writing it first, I'm going to do this by example, keeping those properties in mind, and hopefully it'll be sufficient for us to be okay with why the property is going to work. It's not a proof, but I think it's a good middle ground for our level. So let's take a random number. Let's take 53,428. Actually, I'm going to make it something else, not a 400. I'm going to make it a 100. That's a bad example as well. Let's make it a 300. There we go, 3. I want to know, is this number divisible by 4? Without doing the whole long division, it's going to take me a while. What I'm going to do is I'm going to split this number up into two pieces. One is going to be 53,300, and the other one is then going to be the 28, right? Then I'm going to see this first number as 533 times 100. And then, of course, I have my 28 left that I still need to have there. So now I'm thinking of divisibility by 4. So now I'll note some things. That 4 goes into 100, right? 25 times. And if 4 goes into 100, 4 goes into any multiple of 100. So any number times 100 will automatically work as well. I'm just stacking hundreds. 4 goes into each individual one, so 4 is going to be happy with 533 of them. So this first term is always going to be divisible by 4. Always. So now I have a situation like the bottom property, where I have divisibility with my first number. When I add them up, the divisibility of that larger number is going to depend on whether I have divisibility for the second part. That's what this is saying. So divisibility by 4 into this original number is going to depend, divisibility, it will depend on this second part only. And in this case, this is just one example. In this case, 4 divides into 28, and so I can conclude that 4 will divide into the original number. But for example, let's say this was a 7. Then all of these guys change, right? All of those change. Then I'm splitting my number up the same way. The first part is always going to be happy with 4. 4 is always going to fit perfectly into that. The second number really determines everything. And because 4 does not divide into 27, it's not going to divide into the original as well. So what have we really done here? We have isolated a smaller number coming from the last 2 digits, and we're basing our decision on that small number alone. And because it's a 2-digit number, it's super easy to just look at it and know if it'll be divisible by 4. So let's write that out. A number is divisible by 4 if and only if I'll write it out in a lot of words so it's super clear. The number formed from the rightmost 2 digits, if that is divisible by 4. So for example, I could have a super large number here, 1,323,971. I immediately know that's not divisible by 4, and my reason, you have to give a reason, because 4 does not divide into the number that I get from the last 2 digits. So the whole point of a divisibility test is to very quickly make the decision yes, or conclusion, yes, it's divisible, no, it's not, by looking at a small number. And in the case of 4, that small number is formed from the last 2 digits. All right. How do we feel about the divisibility test for 4? Does it make sense why that is? Again, we just have well, I guess we have 2 examples, one ending in an 8, one ending in a 7. And it's simple enough to hopefully convince you, but understand that that is not a proof that would show that for any number that would work, I need something more general, of course, built on these things. Alrighty. So that is 4. Let's go cross it out. So I want to have a sense of why is the test for 4 what it is, whether I can reproduce that whole explanation, or whether I can just do it by an example. I want something. I don't want to just blindly memorize these tests so that I can use them. I want to have a number sense. I want to have a sense of what makes 4 different from 2 and 5 and all these numbers. They're all different in some way, and some of them are similar and some of them are not. And why is that? Just have a sense. And if you want to dig deeper, of course, then you can. 8 is going to be next. Now, if I try and do the same thing for 8, even if I could be lucky here and maybe get the last 2 digits that is divisible by 8. Let's take a 4 here. And this example is random, which is going to show the risky side of this. So if I look at the last 2 digits and say, well, what if I have something like this? Then I Do I have divisibility by 8? Well, we can sort of cheat a little bit and use our calculator to divide the original number by 8. So 53,324 divided by 8 is, and you see that it is not divisible. 6,665 and a half. So looking at the last two digits when I'm looking for divisibility by 8, let me just update here. I'm a little behind what I'm saying, excuse me. If I then say, well, 8 divides into the last two digits, so does 8 divide into the whole number? No, it doesn't, even though the last two digits work. And it's because 8 doesn't divide into 100. So I'm losing this first part. And then everything that follows that is a little bit of a disaster. So how can we adjust this so that I can have a test for 8? Well, let's take the same number. I just don't want to keep erasing this. We're going to have to pull it apart in a different way. I'm going to take 53,000 and then I'm going to take 324. Then I'm going to see the first number as 53 times 1,000. And of course, my 324 is still there. Now, I couldn't use 100 because 8 didn't divide into 100. But 8 does divide into 1,000. 8 times 125. So that means 8 is going to divide into any multiple of 1,000. So that means that this first part is always divisible by 8. And now I'm back on track, where my divisibility by 8 for the original number is only going to depend on this last number. Where does this number come from? From the last three digits. Then I can look and see, oh, does 8 go into 324? Now, it is a simpler, it's 3 digits, it's unfortunate, but it is a simpler number to look at compared to the original. And I can very easily do that, right? I don't even have to do a full division. 8 goes into 32 4 times. 4 times 8, 32. Then I have 4 left, and I see, no, there's going to be a remainder of 4. So I could say, well, 8 does not divide into 324, and I can then conclude that 8 does not divide into my original. Oops, original, which is 53,324, which could have been way bigger. I still only need to look at the last 3 digits. I don't need to find the quotient. I don't need to do a full division. I just need to know, does 8 fit into that or not? 8 goes into 32, yes, so only 4 is left. Oh, there's going to be something left over. 8 can't fit in. So it's not as nice as 4 in that I need 3 digits, which can slow me down a little bit, but it's not that bad. Let's write that out. Divisibility test for 8. A number, these do get a little wordy, but that's okay, is divisible by 8 if and only if, meaning if it's divisible by 8, then this property is true. If this property is true, it's divisible by 8. It's the only condition I need. The number formed from the last 3 digits, if that is divisible by 8. So we can take another example. I'm just randomly making these up. I don't know if I have something that is divisible by 8. 7, I guess I could fudge it. 720,000. Let's go 440. So I know it works. For this number, I only look at the last 3 digits. And I can quickly do that, right? I'll scribble it to have something to look at. 8 goes into 40 5 times. 5 times 8 is 40. So I have 40 left. So 55 will definitely work. So 8 divides into the original number. My reason? Because 8 divides into the number formed of the last 3 digits. So it is a little slower because it's a 3-digit number instead of a 2-digit number, and it could just require me to pause and just quickly check. Oh, 8 goes into 40, and then 40 is left. Okay, it works. But still, it isn't the same style as the test for 4. For 4, I look at the last 2 digits. For 8, I look at the last 3 digits. So it's still a saving that I'm making. And we're done with 8. How do we feel about the divisibility tests for 4 and 8? It's good to have just a sense of do these things work? And why are they not exactly the same test? What makes 8 different from 4? In 4, I exploited the fact that it divides into 100. For 8, I don't have that, so I need to adjust it a little bit. Let's check a question here in the chat. Mike's muted. Oh, sure. I probably muted your mic because some time ago there was some background noise and I forget to unmute it. I was wondering why you're checking the first 3 numbers if the last 3 are the ones we are checking. Where are we checking the first 3 numbers? I don't know where I did that. Unless I completely missed something, we always check the last 3 numbers. 53 times 1,000. Okay, hold on, let's go there. Yes, we split it up. 53,000. And then what's left? 324. And then because it's times 1,000 and 8 fits into 1,000, I know this first guy is always going to be happy. I need to justify where's this test coming from? It's coming from the fact that 8 fits into 1,000. Therefore, the early digits will be grouped as multiple of 1,000. And 8 will always divide into that. That then tells me that the only thing that decides if this original number is divisible by 8 are the last 3 digits, because the early ones are all going to be connected to this 1,000. I never checked them. I never specifically checked them. I'm trying to justify why the test for 8 is what it is. Because it's not obvious. Why do I have to check the last 3 digits? Why not the last 2 or anything else? And it's really based on the fact that 8 likes this 1,000. So perhaps I'm not understanding your question, but I don't believe we're always checking the last digits. But no, good ask. Yeah, absolutely. I could be missing something as well, because I'm thinking of what comes up and the order in which I need to do these things and all kinds of stuff. So definitely check up on me. So we are running out of numbers here. We're working our way through these very quickly, maybe too quick. Please feel free to stop me if I'm going too fast. Next up is going to be 3. Now, unfortunately, 3 is not going to work like this. You are welcome to try, but It's just not going to be that simple, though it is going to be similar. I'm going to take an example. Now, I don't want the number to be too big, but I don't want it to be too small either. So let's take, I like it in the tens of thousands. I like that size number. Let's take 53,000. Just want to make them all different. 124. That's fine. That's a good number. Nothing wrong with that. So again, I'm using an example to sort of get an idea of where the test comes from. It's not a proof, but it's also not a nothing. Some middle ground, some compromise. Because often these proofs are a little bit too abstract in general. It's hard to get into that kind of style, that language that they're speaking. So looking at specific numbers is going to help me. So it's better than nothing. What I'm going to do is going to pull this apart. My favorite exercise in elementary school, when they pull everything apart and then they write this in words. Oh, that is my least favorite thing ever. Luckily, we're not going to write the word part, but we do want to pull this apart according to the places. What I'm then going to say is the first one is 5 times 10,000, right? The next one is 3 times 1,000. The next one is 1 times 100. Because it's not always going to be a 1, I want to emphasize that it is a multiple of 100. Then it's 2 times 10, and the 4 is just hanging out, waiting to see what on earth is happening here. Okay, now the problem is that 3, which is my focus right now, 3 doesn't divide into 10,000. It doesn't divide into 1,000. It doesn't divide into 100 or 10. So I can't quite exploit this multiple property yet. I need something divisible, then any multiple will always work. Don't have that yet. But I have something nearby. I have the fact that 3 divides into 9, 3 divides into 99, 3 divides into 999, and so on. 9,999. So all I'm going to have to do is just write this 10,000 as 9,999 plus 1. Write this 1,000 as 999 plus 1. I'm going to have to go a new line here. Write the 100 as 99 plus 1. Write the 10 as 9 plus 1. And then I have the 4. I'll just emphasize while I'm thinking of this, this is not something you will ever need to reproduce. But I need to explain or have an idea of why the test is going to be what it is. So that if someone one day asks you, you've seen it before, you can probably come up with this on your own. But having never seen it and just blindly memorizing stuff, no, it's a complete waste of it's a waste of time. We want to have an insight for how these numbers work. What makes 3 different than 2 and all those things. Okay, so now I'm going to multiply the 5 into the bracket. Again, I'm doing this once to see, we'll get an idea. I don't want to do this every time. So 5 times the first one, 5 times 1 is just 5. Then I multiply 3 into the bracket. I don't want to simplify it. I want to see how does 3 fit into the detail that makes this original number. 3 times 1 is 3. Then I will go here, my 1, which doesn't always have to be a 1, so I want to keep track of how that changes. 1 times 1 is 1. Then 2 times 9, and 2 times 1, and 4. Again, if I say 18 here, that doesn't show me anything. I need to pull this number apart. in a way that 3 is happy with some of it at least. Now I'm just going to reorganize this into all these multiplication terms. 3 times 999 will be grouped with this 99, and then the 2 times 9, and then I'll leave a little bit of a space here. What I have not grouped is 5, 3, 1, 2, and 4. I'll put brackets around it. Why not? 2 groupings. These all sort of look similar, right? They have some multiplication in them, and the other ones are just there. So now we have this multiple property again, that if 3 divides into 9, it's going to divide into 2 times 9. If 3 divides into 99, well, 99 is there. If 3 divides into 999, it's going to divide into any multiple of 9,999. So let's get some color here. So my pink grouping is always going to be divisible by 3. And I'm using a combination of these properties. First up, each individual term is a multiple of something that is divisible by 3. And then I add them together. If I add things together that's divisible by 3, they're all together. The answer is going to be divisible by 3 as well. So I really need those 2 properties. So what I have is that only this blue section is what's going to decide if my answer is my original number is divisible by 3. So it only depends, divisibility by 3 of the original only depends on this blue section. And now we can say, well, this blue section is 5 plus 3 is 8, plus 1 is 9, plus 2 is 11, plus 1 is 15. The answer is 15. I notice that 3 divides into 15. I can then conclude that 3 divides into my original number, and I celebrate. So it was a small number to actually use to compare against 3. I'll call that the comparison number. But where does it come from? It is exactly the digits of the original added together. So the number I need to test divisibility by 3 to make a conclusion about the original is a small number, and I get it by adding up the digits. In this case, we added up the digits.
It's blown right now.
That's good. That's the point.
I just was shocked right there.
That is the point. I'm glad. Unless you're being sarcastic.
No, that makes perfect sense.
Yes, to me it makes a very big difference having seen sort of an explanation of where this comes from versus me just writing it down and telling you to memorize it. It's a huge difference. And whether you remember and can reproduce this is beside the point. You've seen it once. You can look it up if you need to. There is a reason. So it's actually quite simple. The process of getting here, that was not that simple. And it wasn't the same. 3, it doesn't behave the same as 4 and 8 in those numbers. We needed to be a little bit more creative in how we're or more detailed in how we pull this number apart. But in the end, the result is very efficient. I just add up all the digits and use that number. If 3 is happy with that number, well, then 3 is happy with the original as well. So let's write that down so we have it in our notes somewhere. So now it's divisibility test for 3. I mean, to me, it's cool, but it's not obvious in any way. I add up the digits. Why? Well, the explanation is a little complicated, perhaps. A number, but the test is super easy to use, is divisible, I have to sound this word out all the time, by 3 if and only if, that's the only test I need, the sum of its digits is divisible by 3. And we can take another example, a random number, I don't know, right? 671,400. Actually, I'm going to make this 21. So you can see here, well, I don't know if the number is divisible, but just looking at the last 3 digits, or last 2 digits, last 3 digits, I can't use those things. It just doesn't work. Maybe it works sometimes and sometimes it doesn't, which means it's not anything reliable. I can't rely on that when it comes to 3. Anything that's going to sometimes work and sometimes not, I can't trust it. It's useless. But that was an ugly C. My comparison number, I'll call it, is going to be 6 plus 7 plus 1 plus 4 plus 2 plus 1. And what is that? That is 13, 14, 18, 21. Oh, it's 21. It's a coincidence. So I can say that 3 divides into my original number, and my reason, 3 divides into this comparison number. Now, this is a bad example. I have to change this. Let's make this something else. Bad example, because now people are going to think, oh, it's the last 2 digits. It's just coincidence that it happens to be the same. So let's change this to, what was it? Let's change it to a 4. Now my comparison number is 13, 17, 21, 23, 24. Okay, there we go. It's not the same. It's not the last digits. Nothing like that. I add up the digits and use that to make my decision. Okay. It was just an unfortunate coincidence that my comparison number was exactly the same as the last digits. And you see that if I explore this example a little further, some people might sit there and think, oh, but if the last 2 digits is divisible by 3 and the number is divisible by 3, that totally works. No, it doesn't. What if I make this 700,000? Then my comparison number is 25. And then it doesn't work anymore, right? It's not divisible by 3 anymore. 3 does not divide into 25. We could use our calculator to double check. 774, 421 divided by 3. It's not divisible. So even though sometimes the last 2 digits or the last 3 digits will be divisible by 3, the number may or may not be divisible by 3, meaning that that is not how I test this at all. The way 4 and 8 work is completely different to how 3 works, which is interesting and something to explore in itself if you happen to be interested. Like, whoa, how do these things work, and which numbers are similar and which numbers are different, and why are they different? It's a world on its own, number theory, that never ends in terms of complexity. So we have crossed out another number, 3. So we have left 6, 7, and 9. Now, actually, I think we have to stop here anyway. Our time's up. But we're really just pausing the discussion. We'll just pick up tomorrow right here. So think about what we've done. See if you have any questions. Bring them to the session. We have time. Why not? But we're just rolling forward slowly, and eventually we'll cover all these numbers and maybe learn something along the way. Who knows? Just want to check because there is some typing in the chat. Sometimes it shows someone's typing and no one's actually typing. Oh, that's nice. Nice to hear. I'm glad you could make this session. So we should be finished tomorrow with this, but I'll double check the schedule. We'll just keep going and see if we're ahead or I don't think we're behind, but we may be ahead of schedule. So that means we have time for questions. Bring your questions. Otherwise, I will stop there and I will hopefully see everyone tomorrow. Until then.
Please remember to click the like button if you enjoyed the video and to subscribe if you want to be notified of more videos. Thank you.